In Part 1 of Module 5, we reviewed ionic and molecular bonds and the concept of electronegativity. We also introduced hydrogen bonds as forces of attraction between two molecules. There are 4 criteria for hydrogen bonds to occur. Firstly, we need 2 molecules with one molecule containing hydrogen that is covalently bonded to either fluorine, oxygen, or nitrogen. The hydrogen will carry a partial positive charge. The second molecule should contain either an oxygen, nitrogen, or fluorine atom with a partial negative charge. The negative and positive charges will get attracted to each other, and a bridge, or a hydrogen bond, will occur between the 2 molecules. Some examples where hydrogen bonds occur include in water molecules, within the secondary structure of proteins, and in the double helix of DNA. After that, we covered the 4 types of biological reactions. Synthesis is to build larger molecules, and it is also called anabolism. Decomposition is to break down molecules into smaller components, and it is called catabolism. Exchange reactions are very common and consist of both synthesis and decomposition reactions. There are 2 examples of exchange reactions. Hydrolysis, which refers to breaking down molecules with the addition of water, and condensation, which refers to building up molecules with the loss of water. The last type of biological reaction is the reversible reaction, which occurs in 2 directions. We also introduced the inorganic acids as proton donors and inorganic bases as proton acceptors. In the second part of Module 5, we covered the biological molecules. First, we introduced carbohydrates and said the monomers are called monosaccharides, for example, glucose. The monomers can join together in a condensation reaction to form polymers. The link between the monomers is called a glycosidic bond. The second type of biological molecule are the lipids. Some of the important functions of lipids include energy and cell membrane structure. After that, we investigated the proteins. The monomers are amino acids, and there are 20 different types. They join by a condensation reaction to produce proteins, and the link is called a peptide bond. Some of the important functions of proteins include reaction catalysis by enzymes. Finally, we discussed the nucleic acids. The monomers are nucleotides, and there are 5 of them. They join together to produce either DNA or RNA polymers. Now let's move to our new topic. In today's module, we will study compounds, chemical equations, and stoichiometry. Module 6 will be covered in 3 videos. The first video will cover the following topics: the mole and molar mass of compounds, percent composition of compounds, and empirical formula versus molecular formula. The second video will discuss how to balance chemical equations and introduce the different types of chemical reactions with special attention to oxidation-reduction reactions. The third video will focus on stoichiometry calculations, determining the limiting reactant, and calculating the theoretical and actual yield of chemical products. The learning outcomes of the first part of Module 6 are: identify mole and molar mass, calculate the percent composition, and determine empirical and molecular formulas. The mass of an atom is far too small to measure on an ordinary balance. For example, the mass of a carbon atom, with an atomic mass of 12.01 AMU, is approximately 2 times 10 to the negative 23 grams, which is too small for even the best laboratory balances to measure. Therefore, chemists measure the mass of a mole of compound, atoms or molecules, rather than mass of one atom or molecule in the laboratory. So what is a mole unit? Mole is the SI unit for atoms. It is a constant number equal to 6.022 times 10 to the 23, which is called Avogadro's number. The mole is a unit for counting, just as a dozen is used to count. To explain the concept of a mole, let's think of the following analogy. A box of 12 eggs is called a dozen. So 6.022 times 10 to the 23 objects is called a mole and is used for atoms and molecules. Why do we need to use the mole unit, and how was Avogadro's number chosen? Scientists discovered that there are 6.022 times 10 to the 23 atoms in exactly 12 grams of carbon-12. So this number was used for convenience. So what is the difference between mole and the unit AMU that we learned previously? AMU is used when we are dealing with single atoms, whereas mole is used when we are dealing with grams of atoms. For example, one atom of carbon-12 weighs exactly 12 AMU. 1 mole of carbon-12 weighs 12 grams and contains 6.022 times 10 to the 23 atoms. 1 atom of hydrogen weighs 1.008 AMU. 1 mole of hydrogen weighs 1.008 grams and contains 6.022 times 10 to the 23 atoms. So to report the mass of one atom, we go to the periodic table and look for the atomic mass and include the unit of AMU. To find how many grams we have in 1 mole of an element, we also go to the periodic table and look for the atomic mass and include the unit grams per mole. This is what we call molar mass. The atomic mass of an element in grams contains Avogadro's number of atoms and is defined as the molar mass of the element. To determine the molar mass, we change the units of the atomic mass, found in the periodic table, from AMU to grams. For example, sulfur has an atomic mass of 32.07 AMU, which is 1 sulfur atom. So 1 mole of sulfur contains 6.022 times 10 to the 23 sulfur atoms and has a molar mass of 32.07 grams. Magnesium has an atomic mass of 24.31 AMU. So 1 mole of magnesium contains 6.022 times 10 to the 23 magnesium atoms and has a molar mass of 24.31 grams. For a compound with known formula, the molar mass of the compound is the sum of the molar masses of all the atoms in the formula. To calculate the moles, we use the following formula. Moles equals mass in grams over the molar mass in grams per mole. Let's practice some examples to learn how to use this formula. What is the molar mass of water? From the periodic table, we can see that 1 mole of oxygen weighs 16 grams and hydrogens weigh 1.00 grams each. So for water, 16 grams plus 1.008 grams plus 1.008 grams equals 18.02 grams per mole. Let's see another example. Calculate the molar mass of calcium hydroxide, which is CaOH2. From the periodic table, calcium is equal to 40.08 grams, oxygen is 16 grams, and hydrogen is 1.008 grams. We have 1 calcium, 2 oxygens, and 2 hydrogens in the compound. So the molar mass is equal to 40.08 grams plus 2 times 16 grams plus 2 times 1.008 grams, which totals 74.10 grams per mole. Now let's look at another example. How many moles are there in 25 grams of iron? To calculate the moles of iron, we need to find the molar mass of the iron. From the periodic table, the molar mass of iron is 56.85 grams per mole. Therefore, moles equals 25 grams over 56.85 grams per mole, which will equal 0.448 moles. Another example. How many atoms are there in 5 grams of magnesium? To do these types of questions, we need to calculate how many moles we have. Then we can use Avogadro's number to calculate the number of atoms. From the periodic table, the molar mass of magnesium is 24.31 grams per mole. Therefore, a mole is equal to 5 grams over 24.31 grams per mole, which is equal to 0.206 moles. We know that 1 mole is equal to 6.022 times 10 to the 23 atoms. However, we don't have 1 mole, we have 0.206 moles. So, 0.206 moles times 6.022 times 10 to the 23 is equal to 1.24 times 10 to the 23 magnesium atoms. Now, how can we calculate the mass of one atom of carbon? We know that the molar mass of the carbon is 12 grams per mole, and that 1 mole equals 6.022 times 10 to the 23 atoms. Therefore, the mass of one atom is equal to 12 grams over 6.022 times 10 to the 23, which is equal to 1.994 times 10 to the negative 23 grams. Another example, what is the mass of 3.01 times 10 to the 23 atoms of sodium? Remember that 1 mole equals 6.022 times 10 to the 23 atoms, but we only have 3.01 times 10 to the 23 atoms, so we have less than 1 mole. So 3.01 times 10 to the 23 over 6.022 times 10 to the 23 is equal to 0.5 moles of sodium atoms. From the periodic table, the molar mass is equal to 22.99 grams per mole. Mass is equal to moles times molar mass. Therefore, 0.50 moles times 22.99 grams per mole is equal to 11.5 grams. Please practice the weekly exercises, and we will cover additional examples in the tutorial. The next topic in today's lecture is the percent composition of compounds. The percent composition of a compound is the mass percent of each element in the compound. For example, what is the mass percent composition of a water molecule H2O? First, we calculate the molar mass, 16 grams plus 2 times 1.008 grams is equal to 18.02 grams. So in that 18 grams, 16 is coming from oxygen. So the mass percent of oxygen is 16 divided by 18.02 times 100%, which is equal to 88.79%. For the hydrogen, it is 2.016 divided by 18.02 times 100%, which equals 11.19%. What is the mass percent composition of K2SO4? The molar mass of the compound is 174.3 grams per mole. The mass percentage of potassium is 2 times 39.1 over 174.3 multiplied by 100%, which is equal to 44.87%. The mass percentage of sulfur is 32.07 over 174.3 multiplied by 100%, which is equal to 18.4%. The mass percentage of oxygen is 4 multiplied by 16 over 174.3 multiplied by 100%, which is 36.72%. What if the question was asked in the opposite way? For instance, predict the compound formula if you know the percentage composition of the elements. To do similar questions like this, we need to discuss the empirical formula and molecular formula concepts. The empirical formula provides the smallest ratio of atoms present in a compound. On the other hand, the molecular formula is the true formula, representing the total number of atoms of each element present in one molecule of a compound. For example, acetylene has the formula C2H2, and benzene has the formula C6H6. They both have a percent composition of 92.3% carbon and 7.7% hydrogen. The ratio is 1 to 1. Therefore, the empirical formula for those two compounds is CH. So when we have the percent composition of a compound, we can only determine the empirical formula, and we cannot determine what the actual compound is unless we obtain more information, which will be discussed later. To learn how to calculate the empirical formulas, we need to follow 4 steps. 1. We assume a definite starting quantity, usually 100 grams, of the compound. 2. We convert the grams of each element into moles, using each element's molar mass. 3. We divide each value obtained in step 2 by the smallest of these values. And the last step, if the numbers obtained in step 3 are not whole numbers, we multiply the values by the smallest number that will convert them to whole numbers. Those steps can be organized in a table to make the process easier. Let's practice some examples. The analysis of a salt shows that it contains, by mass, 56.58% potassium, 8.68% carbon, and 34.73% oxygen. Calculate the empirical formula for this substance. So, to determine the empirical formula from the percent composition, we can use the following table. In the first row, we put the mass percent, which is given in the question. In the second row, we convert from mass percent to mass in grams by assuming we have 100 grams of the total sample. In the third row, we calculate the number of moles. To do that, we need to divide the mass over the molar mass, which we can get from the periodic table. From the periodic table, you can find that potassium has a molar mass of 39.1 grams per mole. Carbon is 12, and oxygen is 16. Therefore, the number of moles for each element is 1.447, 0.723, and 2.171 respectively. Now, we have the number of moles for each element. The last row is to calculate the ratio of the elements in the compound. To do that, we divide the moles of the elements by the smallest number. In this example, carbon has the smallest number of moles, so we divide by 0.723. So the ratio of the elements is 2 for potassium, 1 for carbon, and 3 for oxygen, which means there are 2 potassiums, 1 carbon, and 3 oxygens in the compound. Therefore, you can determine the empirical formula as K2CO3. Let's look at another example. Propylene has a molar mass of 42.08 grams and contains, by mass, 14.3% hydrogen and 85.7% carbon. What is its molecular formula? To do that, we need to determine the empirical formula first, then we can calculate the molecular formula. We use the same table plan. Calculate to grams by assuming you have 100 grams of sample. Calculate number of moles by dividing mass over molar mass. divide by the smallest number of moles, which is the carbon, the ratio is 1 to 2. So we have 1 carbon and 2 hydrogens, and the empirical formula is CH2. However, we need to determine the molecular formula. This compound can be anything that meets the 1 to 2 ratio. For example, it could be C2H4, C3H6, C4H8, and so on. Therefore, we need more details to determine the molecular formula. Remember from the example, we got the molar mass of the compound as 42.08 grams. The molar mass for the empirical formula, CH2, is 12.01 grams plus 2 times 1.008 grams, which is equal to 14.03 grams. So if you divide 42.08 over 14.03, the answer is 3. So the actual compound is 3 times heavier than the empirical formula. Therefore, you can say that the molecular formula is 3 times CH2, which is C3H6. This is the end of part 1 of module 6. Please proceed to part 2, which will cover how to balance chemical equations, discuss some types of chemical reactions, and will show you how to balance oxidation and reduction reactions.